Ladies and gentlemen, welcome to machine learning. In this video, we will be talking about generalization. So the ability of our model to predict well for inputs it did not see in training. And after we do a little bit of derivation, we will find the Bias-Variance Trade-off. Let's jump right in. So in the last videos, we talked about that the difficulty of machine learning is to find models that generalize well. And if we have now a model, we would like to predict the performance of that model. So let's look at our first example right here. We have a sine curve that generates our data, and our data points are now the purple dots. And we propose now a function. In this case, it is a linear function. And this is the best plot we can come up with the help, for example, with the linear least squares. So we see that if we have a function like this, it will not approximate our sine curve very well. So we say we are now in the underfitting regime. So our model, our linear function that we proposed, is not complex enough to capture our data generating process, which is our sine curve. If we, on the other hand, propose a polynomial that has, for example, degree 9, if we have 9 data points, we will be able to fit our function through every data point and thus have a training error of 0. So we will be able to basically fit our function perfectly to the data. But you see that if we have a training error of 0, we do not have the sine function. So we do not find the sine curve if we have a very, very simple model, and we do not find the sine function that with a very complex model. So the complexity here is the degree of the polynomial. So we will have to find a middle ground where we have a model that is complex enough to approximate our data generating process, but not too complex, so it can randomly just learn the noise in the data and get a fit of something like this. So this is the most difficult part in machine learning because we said that we can propose very, very simple models and we can propose very complex models that can learn simply the mapping from input to output and not the data generating process that is behind this data. So when we talk about performance, we can basically introduce something so that captures our performance in theory. So let's assume we have a true relationship between our input and output. So our output is y, our label, and that is a function g. In that case, that was the sine curve and some noise. So the noise is why our data points are not exactly on our sine curve. So we have some noise in our data. The mean of that noise is assumed to be 0, and the variance is constant sigma squared. So if we have now many, many data points for 1x, we will get the many values y, and we assume that we will get the true data generating function. This is what we saw in the last videos. So for example, if we have Gaussian noise, this is not a very good Gauss curve, looks something like this. So on average, we will perfectly fit our data generating function if we have many observations for one specific x. Let's make it x star. So, and now we try with our machine learning model, we try to learn our data generating process. So we try to approximate and learn our g of x with a model. Now we define our expected performance, and we call it our expected loss or our expected risk. So how good will our model be after we trained it? So we define a risk, that is the expected loss, so an expectation over the loss function. And by the definition of the expectation, we have our loss function, and we take the average over our data, so over x and y. So we have a double integral. So we have our loss, probability of x and y over the x and the y. So L here is our loss function, and we will show that in the optimal case, so y hat is equal to our g of x. So in the best case scenario, the risk or the expected loss will be the lowest if our function is our true data generating function. This is all good, but the problem is that we don't have the probability of p and x, of the probability of x and y, because we have only a small sample of this distribution and we cannot get to this function. So this is something that is only available in theory and not in practice, because we don't have access to the probability of x and y. But we will still be able to work around it a little bit and see and break this function down basically and see what parts are hidden in this loss function or expected loss. So let's say that we propose a loss that is the predicted value minus the true value squared. So this will be our square loss estimator. This square loss estimator is not related to the loss or cost function that we optimized in the training process. So this can be a completely different process and has nothing to do with the function that we optimized when we got our parameters, W, for example, so our weights. So now we can say that we want to get the expectation of our loss function, and we want the loss, so we insert the loss into our expectation, and we get this expression. Now we can add and subtract our true data generating process, and it will still be the same. Now we can expand our bracket, so we get rid of the square, and we will have now 3 terms. So the first one is y hat minus g, the second one is g minus y, and the third term is 2 times y minus g times g minus y. So g hat is our optimal case where g is equal to y hat. So y hat is our predicted value and y is our true value. So now let's get rid of this and only look at our second term. So what is the expected value of g minus y? So y is our true value and g is our expected, our true data generating process. We see, or we remember, that y is actually g plus epsilon. So we have g minus g plus epsilon. And this will be g minus g is 0. So that's why we have the expected loss of our just noise. And this is the exact term of the variance plus our expected value of the noise squared. And we see that this part of our expected loss is just our variance. So we already see that if we have an expected loss that we're calculating, the expected loss will never go lower than our variance in the noise of the data itself. So we will never be able to have an expected loss of 0. Now let's look at the second term and the first term. So again, this was the second term right here, where we have the 2, but we just remove the 2 for now. So we have y hat minus g times g minus y. Y is now the true and y hat is the predicted. So again, by the definition of the expectation, we have a double integral where we have the first one and the second term, and we take the expected loss over our data. Now we can expand our px and y into py given x times px. So this is the rule that we had in the recap of probability theory, where we had the joint probability of p, x, and y is equal to probability of x given y times probability of y. Or in this case, we have everything just switched with an x. So this is how we got the second line. And now we see that we have these 2 terms, and we multiply this term first with our y and with our g, and take the integral over y. G of x is not dependent on our integral and not dependent on y, and y times the probability of y given x integrated over dy is equal to just the expected value of y given x, because that's the definition of the probability. In the case of the g, the probability of y given x over dy is just simply 1, and So the g of x is not dependent on y, so we can just factor it out and not subtract, but insert our value that we had before from here, that g of x is the expected value y given ax. And we see that these two terms cancel out and we get a 0. So this term in our expanded expected loss will be 0. So we are left with only the first term from here, and we will have a expected loss that is equal to our predicted value minus our true data generating process squared plus some noise from plus a constant vector that plus a constant value that comes from the noise of our data. And we see that if our predicted value y hat is our true data generating process, our expected loss will be equal to the variance of the noise. So in the optimal case, we will just have that, and we will never be able to get lower than the expected, lower than the variance of our noise. So sigma squared is an irreducible component of the expected loss. Now we come to the bias variance decomposition. So in practice, we have only a finite amount of data. So this was all done with technically infinitely amount of data, but in practice, we only have finite amount of data. So our values or our probability of y given x are also dependent on the data that we're having. So now we introduce an average estimator that is averaged over all possible training data sets. So imagine that we're having infinite amount of data and we take sections of it and train our model. And then as soon as we have that model, we average all those models, and this will be our y hat average, so the average prediction. Now we take, let's get rid of all this. Now we take this part in our expected loss and rewrite it back here and do the same trick we did before, where we added the average estimator. So we subtracted the we subtracted the average estimator and added the expected estimator. So we didn't change nothing. Then we remove the squared and just write the expansion. So we have y hat minus average plus average minus g squared and this term. So now let's look at the last term now. So what is the expected value of over our data of that term? So we see that y average is not dependent on the data because it was already averaged. So the only part here is our y hat. Here we have the y average, which is also not dependent on the data because it already was averaged, and g of x, which is also not dependent on the data because it's the true data generating process. So we can take these two, put them to the front. The 2 is also not dependent on the data, so we can put it to the front. And what we are left with is y hat minus y hat average. So if we now take the average over the data, the y hat will turn to y hat average. And y hat average minus average will be equal to 0. So as soon as we do that averaging over all the data, this term will vanish, and we're only left with these two terms. Now we come to the actual bias variance decomposition. So our term that was left from here, our term that we had from here, this one, is now just y hat minus the average squared plus the average minus g. Why do we not have the average here over the data? Because these two terms are not dependent on the data. And if we now insert this into our expected loss, we will see that we have the average over, or the expected value of our average minus the true data generating process. And this from here, we will have the expected value of our expectation over all possible data of y hat minus y average squared and the noise that we found from the last term. So now we can have the bias, variance, and noise. So now we will talk, well, what is the bias, what is the variance, and what is actually the noise? So the bias in this term is the measure to the extent which the average prediction over all training data sets, so the average prediction over all data sets, differs from the desired regression function, so from our g of x. And we say that models that have a high bias are therefore too simple. So high bias means, let's say bias is high is equal to simple. So this will be this exact case where we have a high bias because our model is too simple. In the other case, we have the variance. So the variance is a measure to the extent which the estimator, so our y, for a particular training data set varies from the average one. So we have the average data, the average predictor, and the predictor on one specific data set. So if we have a high variance, what does it mean? That means that our model is very sensitive to that particular data. So if we have one data set and we have a very, very complex model and we train it, and then we train it again on another data set with the same model, we will get a completely different model. So we have this example from before. Let's have a look. This example from before. Let's zoom in a little. So if we, for example, remove that point and add another data point right here, the yellow graph that we get would be completely different. And that means that our result is very, very dependent on the data that we're having. One option to get rid of the variance is to increase the training data. So if we want to reduce the variance of the model, we can just simply increase the data size. So increasing the model complexity, to summarize, will increase the variance. So high variance is overfitting. And now the goal is, well, how can we minimize both the bias and the variance term? Because decreasing or increasing our complexity will decrease the bias while we're increasing the variance. So in this case, let's go again back, we are too simple and we have a high bias. In this case, we have a low bias, but a very high variance, and we would need to find this middle ground. So this is our dilemma. So we have the bias-variance trade-off. This is a very, very difficult problem to solve, and in the next videos, we will talk more about the bias and the variance. If you have any questions regarding the derivation, I hope you could more or less understand what it's all about. The most important part to understand is this one right here, that we have a bias, a variance, and they are in relation to each other. So we cannot just simply increase one while the other one stays constant. They are both not independent of one another. If you have any questions, feel free to ask them in the comments down below. Thank you very much for your attention, and I'll see you next time.